A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians. Welcome back to another video. Today we are going to talk asymptotes. Why? Because asymptotes and asymptotics are a lot of fun. And I hope you are going to enjoy the video, which has been sponsored by the wonderful people over in Brian. More information at the end of the video, and I beg you, please watch the entirety of this video. It seriously supports the creators a lot. Even if you are not a Patreon member, for example, just watch the entirety of the video and everything's nice. That's gonna be cool. Gonna be recommended to the algorithm more, and that would mean the world to me. Thank you very much. Now, asymptotes are some of the coolest stuff I like to teach to my students because at first they are kind of counterintuitive, and one of the first applications of limits that I teach to my students when it comes to limits at infinity. And maybe you are familiar with asymptotes, and maybe you are not. Maybe you have never heard of curvilinear asymptotes before. I'm gonna talk about everything a tiny little bit today, and I hope you are seriously going to enjoy the video because I really enjoy the topic, and I'm trying to make those videos as enjoyable as I can for you guys. So at first, a tiny little introduction. Now, regular functions, for example, just the identity x, what they do is they grow to infinity, for example, back and forth, positive and negative infinity. But there are other classes of functions which have a few quirky properties. And one of the prime examples, which I also show to my students, is just f of x being equal to 1 over x. Now, you are probably already familiar with this function. That's the so-called hyperbola. And what does the graph of the hyperbola look like? Well, what we get is we get two branches of the hyperbola, and it kind of looks like this. And the special thing about this function is that we get areas in the domain and also the codomain, which we can not hit. Like if we take a look at x being equal to 0, which is the y-axis, our function is creeping up on it, but it just doesn't touch it. It's not in the domain. It's not defined at 0. And this is what we call a vertical asymptote. It goes in the vertical direction. And this is a point of the function where it's not defined. It's creeping up on it. It's trying to creep up on it from the positive direction, also the negative direction, but it really doesn't hit. It goes around a circle, basically, and it goes back. So if you imagine it on a sphere, this hyperbola, it goes there, goes around, and then comes up once again, blah, 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 and back. But it doesn't touch 0, only at infinity, you could say. Same thing with y being equal to 0. This is a so-called horizontal asymptote. It's creeping up on the x-axis, but it doesn't touch it. Only at infinity, you could say, approximately. Limits are just a concept, okay? Doesn't really work like that you can go over there and see infinity. But theoretically, at infinity, you are going to get a value out. Namely, y being equal to 0 for x going to positive or negative infinity. Now, those are two types of asymptotes, and this not only happens on rational functions, where a rational function is just a quotient of polynomials. No, it also happens, for example, with transcendental functions, for example, f of x being equal to e to the x. We are all familiar with the exponential function, and what it does, it has a horizontal asymptote, once again at y being equal to 0 for x to negative infinity. It creeps up on the x-axis, but over here, for x to positive infinity, it really doesn't have an asymptote, it just diverges to infinity. This is what the exponential function does as a transcendental functions. And today, I would like to take a look at rational functions because they are kinda interesting when it comes to asymptotes. And we are going to talk about a few cases. And as mentioned before, rational functions are just defined as the quotient of polynomials. And what are polynomials mainly defined by? By their degree, where the degree of a polynomial is just the exponent with the highest number, basically, on a summation of unknowns x, or powers of unknown numbers x, or unknown variables and their coefficients. That's what a polynomial is, over a certain field. Now, we can have three main cases, basically. Namely, that the degree of the numerator is higher than the degree of the denominator, or vice versa, or that the degree of the numerator is the same as the degree of the denominator. Now, let us just start with the last case that I just talked about, namely the degree of the denominator is the same as the degree of the numerator. And I'm just going to pull some stuff out of my ass. So f of x is equal to, for example, 3x squared divided by x squared minus 2. Now, what we're going to do is we are going to see how this function is going to behave when x goes to, we are going to take a look at it exclusive to positive infinity. Most of the time they are kind of symmetric in some kind of way. So what is going to happen is the limiting value for x to negative infinity is kind of the same. It's a case study, okay? You can also take it to negative infinity and see what you're going to get. Now the main procedure here is probably very familiar to you if you have ever done calculus. So if we take the limit as x approaches infinity, I'm going to denote it as capital L of this function. What we are going to do is we are going to algebraically manipulate this quotient of polynomials in such a way that most of the stuff goes to 0. And the cool thing about infinity as a concept is that if we have 1 over infinity, this goes to 0 because the larger the denominator grows, the smaller the number in itself gets. So what we are going to do is we are going to factor out the highest power of x on both the numerator and denominator, and then we are going to use limiting rules to kind of get rid of everything that we don't want. So I'm going to factor out the x squared on both numerator and denominator, leaving us with x squared times 3. Might sound basically redundant what I'm doing here at the moment, but it does make sense in a second. Also, we need the limit as x approaches infinity. Factoring out the x squared here leaves us with 1 minus 2 over x squared. Okay, now the cool thing about limits is that we can algebraically manipulate inside of the limit. So this right here is going to cancel out. Now, if the limit does exist on both the numerator and denominator for x to infinity, we can actually distribute the limit to both the numerator and denominator. That's the limiting rule. Now the limit of the numerator is just gonna be 3. It's not affected because it's a constant. Now if we take the limit of this difference down here, 1 is also not affected, it's a constant. And then the limit as x approaches infinity of 2 over x squared is the thing that I just talked about, namely, if the denominator goes to infinity, the entire thing goes to 0. So this right here is going to die somewhere in Mexico, gonna go to 0. So the limiting value is 3 over 1. Now this right here is the really cool case because there's a really easy mnemonic device. If the degree of the numerator is the same as the degree of the denominator, then the limiting value for x to infinity is just going to be the quotient of the leading coefficients of the highest power of x, namely 3 over 1. There's a 1 in front of the x squared down here. And that is very easy. Now, what does it mean to have the limiting value of 3 over 1, which is nothing other than 3? Well, if you take a look at the graph of this hyperbola, of this rational function, you're going to notice that we have a horizontal asymptote exactly at 3. And this is basically what it means. Well, that's nice. If we get a certain value out, it's going to be a horizontal asymptote. Just like here, it has a horizontal asymptote at y being equal to 0. Now, next case that we are going to take a look at is f of x being equal to, and now I'm just going to make a tiny little difference. I'm going to get rid of the squared up here and just say 3x divided by x squared minus 2. Degree of the polynomial in the numerator is lower than the degree of the polynomial in the denominator. And once again, what we are going to do is we're going to go through the same procedure of factoring out x squared on both numerator and denominator because it's the highest degree, and then distribute the limit into everything. So we take the limit as x approaches infinity of all of that. If we factor out x squared, we are going to be left with 3 over x in the numerator. And down here, what we are going to get is 1 minus, and we notice, 2 over x squared in the denominator. Now taking the limit here, 3 over x is going to go to 0 once again, because it's 3 divided by infinity. Basically, this right here is also going to be 0. So the limit goes to 0 divided by 1, which is 0. And as mentioned before, if we get a concrete number out, we are going to have a horizontal asymptote. Look at that. It should have worked out, even though I just pulled something out of my arse here. So it basically has the same horizontal asymptote as our hyperbola here. And this is always the case. If the degree of the numerator is lower than the degree of the denominator, we are going to have a horizontal asymptote at 0. Same with 1 over x. That's a polynomial of the 0th degree. Of the 0th degree, basically. And this right here is going to be a polynomial of the 1st degree. So, yeah, it's the same relationship. And now, here comes the really fun part in. Namely, if we switch this around. F of x is equal to x squared minus 2 divided by 3x. Now this right here is the really, really fun part about asymptotes. Because if we go through the same procedure once again, what is going to happen is we are just going to change this relationship around. So 1 minus 2 divided by x squared divided by 3 over x. And now you're going to notice something peculiar. Namely, this right here goes to 0. This right here also goes to 0. But hell no, Papa Flemmy, this doesn't diverge. This is 1 over 0, basically. And this goes to positive infinity. That ain't good, right? Now, look at the graph of this thing. Are you noticing something with the asymptote? There is one, but we don't get a concrete value out. It's not a horizontal asymptote. It's something different. Now, if I just take a look at this relationship right here, I'm not having the graph of the thing in front of my eyes, but I can tell you that the asymptote probably is a slant asymptote or oblique asymptote. If you take a look at the graph, you are going to notice that if you plot a linear function into there, then it's gonna kiss our original rational function somewhere at positive and negative infinity. There are different types of asymptotes. So we can have this relationship like we do here, where we have this function like this. And if we plot the linear function into here, we are going to have this as our asymptote. A linear function, which is going to be basically the remainder term. What I'm talking about here, I'm going to get more into detail in a second. Now we can also have a different kind of asymptote, and this is called a curvilinear asymptote, and they can have a degree of 2, 3, 4, 5, and so on. Point is that if we have a rational function like this, notice something? What we could do is we could put a parabola on here and notice that it's going to kiss our function somewhere at positive and negative infinity. You can also have this with the 3rd degree and so on, as mentioned before. But point is, our asymptotes can take many different shapes and forms. They are going to be in some kind of way polynomials once again. They are going to be remainder terms. They are going to be approximate forms of our original functions. And this is going to be demonstrated right here. Now what we do here basically is we take the quotient of two polynomials. Well, what is this exactly? That's called polynomial division. I mean, if we divide polynomials, it's going to be polynomial division. Now here is one sad fact. Papa Flemmy always forgets how to do polynomial division because he's an absolute dumbass. But this is not a problem because just take a look at what I'm doing here now. If we divide, for example, our polynomial here, x squared minus 2, by the other polynomial, 3x. What we are going to do is we are going to get another polynomial out on the other side, p of x. Okay, it does make sense. If we divide a number by a number, real number by real number, we are going to get a real number out. For example, if we divide polynomial by polynomial in a ring, we are going to get another polynomial out. What we can also do is we can solve this right here a tiny little bit for our original function that we have in the numerator by multiplying both sides by 3x under the condition that it's not equal to 0. So we need to not include x being equal to 0 in our calculations or our argumentation, but this is not the case at all because this function right here already has a vertical asymptote at 0. It's just like here, a vertical asymptote is just where the domain has kind of jump. It doesn't exist there, our domain is not defined there. So 0 is not a problem whatsoever. So we can reformulate this into how can we express x squared minus 2 by 3x times some other polynomial p of x. And we can do a bit of assumption work here for our polynomial p of x. Well, we need to get to a degree 2 polynomial on the left-hand side. Now, what must our polynomial be then? Well, it must be, I'm terribly sorry, a degree 1 polynomial, because multiplying degree 1 by degree 1 gives us at most degree 2. So our p of x is something of the form ax plus b, basically. But here's where division comes in, and also polynomial divisions. What we also get is, maybe in some cases, a remainder term. Now, if you take a look at, for example, x squared minus 9 divided by x plus 3, that's an easy polynomial division, because we can turn x squared minus 9 as the difference of two squares into the linear factorization as x plus 3 times x minus 3 divided by x plus 3. By cancelling this out, polynomial division leads us to x minus 3 overall. But this is not always the case. Sometimes we have a remainder term. Just like if you divide 11 by 5, you are going to get 2 with a remainder of 1. Same with polynomials and polynomial division. Now, what we must do to get this remainder term is we basically just get a polynomial p of x plus a remainder r of x. This is all we really need to do. So let us try to go at it. We must express x squared minus 2 as 3 times x times ax plus b plus 3 times x times r of x, where r of x is our remainder. Now, we can also do another assumption here. This right here is a monic polynomial on the left-hand side, meaning the leading coefficient is going to be 1. The only way to arrive at 1 by multiplying those two together is going to be by having a being equal to 1/3, because 3 times 1/3 is going to be 1 overall. This really makes it a tiny little bit easier. Now, by multiplying everything out, we are going to get, by this assumption, x squared, and then we are going to get plus, and now we have 3 times b times x, 3bx, plus 3 times x times a remainder with respect to x. Now, we just need to compare coefficients now, and we need to play around with the remainder a tiny little bit, because we want to go, or we want to get ultimately to this side right here. X squared already fits the bill. So what we need to do is we need to turn this part that we have right here exactly into 2. Now, there are two things in our way exactly for this to happen. Namely, we have this term with x right here, and we also have the multiplication of something that we don't know about, and 3 times x here. Now, we can easily fix this problem by saying that, what about having, for example, r of x to be equal to 2 and b to be equal to 0. This is something that could ultimately work out if we have b being equal to 0. This part is going to vanish. We are going to get rid of the x part. And now we just need to have that 2 is equal to 3 times x times the remainder of x. Now, the only thing left to do is we are going to divide both sides by 3x. So meaning that the remainder polynomial is going to be 2 divided by 3x. Meaning overall, by doing our polynomial division, what we are going to get ultimately is a polynomial which is of the form of a linear function ax plus b, where a is equal to 1/3, b is equal to 0, plus our remainder term. So x squared minus 2 can be expressed overall as, x squared minus 2 divided by 3x, I'm terribly sorry, which is our original function, f of x, can be expressed as a is equal to 1/3 x, and then we are going to get plus 2 divided by 3x. Now, how is this going to help? Well, I want you guys to remember that we basically want to take the limit as x approaches infinity. And as mentioned at the very beginning, this asymptotic stuff is basically just an approximation, how our function is going to behave basically at infinity. And those two functions are equal. Overall, they are also asymptotically equal, meaning what we are going to do is if we take the limit as x approaches infinity of our original function f divided by that thing that we have right here, 1/3 x plus 2 over 3x. This right here is going to approach 1. They are the same function overall. this divided by this is going to be equal to 1. Limit of 1 is going to be equal to 1. We call those two functions asymptotically equal. But now here's where the magic happens. If we distribute the limit into the denominator, you're going to notice that just like the argumentation that we have before, this part is going to vanish. It's going to go to 0. Meaning overall that f is also asymptotically equal to 1/3 x. And if we now plot this function x squared minus 2 divided by 3x together with 1/3 x, you're going to notice that 1/3 x is most probably, I hope I didn't fuck stuff up because this is completely improvised, as our as our slant or oblique asymptote. And you can go through the same process here and do some other stuff. For example, you can get yourself a function 3x cubed plus 2x squared plus x plus 1 divided by x. This right here is a function. And now, this thing right here, by the same argumentation, our polynomial that we are going to get mainly is going to be x cubed divided by x. Asymptotically, it must be a parabola overall, because this right here, x squared divided by x, turned into a linear function as the asymptote. So this right here is going to be a parabola, meaning overall, this is going to turn into something like this right here. This scenario, I don't know what the function looks like. Let's just take a look at the function right here. Okay, it's going to be a curvilinear asymptote of degree 2. I'm going to erase a tiny little bit of stuff, and we are going to go through our procedure once again with the polynomial division that I had here. So what we are going to do is we are going to express 3x cubed plus 2x squared plus x plus 1 as a polynomial. We know it's going to be of second degree because of the argumentation that we did here. So meaning we are going to take x times, okay, this polynomial is going to be of the form ax squared plus bx plus c plus a remainder polynomial. Now we are going to make our life easier once again. A must be equal to 1 because x times x squared is going to be, no, it must be equal to 3 because I have a 3 in front. It's going to be equal to 3 because then we are going to get 3x cubed out. And now we are just going to juggle everything in and see what we are going to get. So we are going to get 3x cubed. This is nice. This is what we need. And also we are going to get plus, this is going to go to bx squared plus zx plus x times r of x. Now we are going to compare coefficients. B must be equal to 2, obviously. C must be equal to 1. And we must have 1 being equal to x times r of x. And this is going to be the easy part, because what we're going to do is we're going to divide both sides by x, meaning r of x, our remainder polynomial, must be equal to 1 over x. In the limiting process, this remainder once again is going to vanish, because 1 over infinity, approximately. This time, this is going to die in Mexico somewhere, meaning we are going to get a curvilinear asymptote at that with the equation. Let's just plug everything in. 3x squared, okay, because this right here is the polynomial we are seeking after, then plus 2 times x plus, and now c is equal to 1. And if I plot the original function and also this parabola into here, it should have worked out, and I hope, I pray to God that it worked out, because otherwise I'm gonna look like an absolute idiot. And this is why asymptotes are a whole lot of fun, because you can play around with polynomials, for example, and train your polynomial division skills that you don't have, just like your virtual daddy. And I hope you enjoyed what you have seen today. And if you did, you should also check out the contents of today's sponsor, Brilliant, who are kind enough to sponsor yet another video here on this channel. Woo! I really enjoyed this one. That is fun. And I really enjoyed to put some Desmos graphs into here, because graphs are going to be a big part of calculus. If I see my students struggling with limits, I always tell them, draw the graph. It's going to be easier for you to find limits, especially at positive and negative infinity. Especially if it's just school examples and just basic stuff. And graphics, a lot of the time, are also in higher mathematics the way to go, be it in statistics, stochastics, or analysis in general. And this is where Brilliant comes in. Brilliant has some of the best online learning content that you can find out there on the internet. It really doesn't matter what you want to learn today in the STEM field, be it the mathematics that we did today, physics, computer sciences, chemistry, everything. They cover everything. And the best thing about Brilliant is that they do those amazing courses with all the abstract stuff that we did here, but they include graphics and visuals and interactive stuff that you can play around with to get a better understanding of the problems at hand. And this is what I really seriously enjoy about Brilliant. They are so innovative with their courses and just with everything that you could imagine. It's seriously cool. It's seriously cool what they have to offer. I love to present their geometry section to my students in 6th grade and also 8th and 9th grade, because it's just so much easier to understand triangles and trigonometry if you have all those graphics that you can play around with, drag the corners around and see what connection is there between the sine and the angle and, for example, the side lengths of a triangle or just the sum of the interior angles. It always adds up to 180 degrees. It's just amazing what they have to offer, and their visualizations are just top-notch. I really love it and I recommend it highly to you. Use my link at the top of the description, brilliant.org/vamblers, to get 30-day free trial of amazing awesomeness. Try the whole landscape of Brilliant for completely free and see if it's something for you. And if it is, then make serious use of my link here down there in the description. And if you do so, you are going to get 20% off an annual premium subscription, which is an amazing deal. They're adding new stuff on a regular basis, and they always brush up on those old courses that they already have and try to make them better for you as the user. They also have their courses as an app, or Brilliant in general. So check out their app too, and also you can use my QR code somewhere up here in the corner to get to my link. So just try it out, check it out, and support the channel this way. It's seriously worth it. Try it out. I recommend it for the life of it. It's seriously cool. Support the channel this way highly, and I thank you guys for watching. I hope you did enjoy this video as much as I did teaching you guys, and I wish you guys a favorable day. See ya!